Alright, so in this video I'm gonna be explaining another important article for graph representation learning with the title Simplifying Graph New Convolutional Networks. So this paper in 2019. Graph convolutional networks and their variants have experienced significant attention and have become the de facto methods for learning graph representations. GCNs derive inspiration primarily from recent deep learning approaches and as a result may inherit unnecessary complexity and redundant computation. So we reduce this excess complexity through successively removing nonlinearities and collapsing weight matrices between consecutive layers. We theoretically analyze the resulting linear model and show that it corresponds to a fixed low-pass filter followed by a linear classifier. Notably, our experimental evaluation demonstrates that these simplifications do not negatively impact accuracy in many downstream applications. Moreover, the resulting model scales to larger datasets, is naturally interpretable, and yields up to 2 orders of magnitude speed up over fast GCN. So you see the schematic layout of a graph convolutional network versus SGC, versus simplified graph convolution. So the GCN transforms the feature vectors repeatedly through k layers and then applies a linear classifier on a final representation. The SGC reduces the entire procedure to a simple feature propagation step, followed by a standard logistic regression. So instead of k layers, you just multiply matrix S k times, and that's it, and then you give the softmax. Because here we have a simple just logistic regression. It's a nonlinearity is at the end. After you have done this k times multiplication of S matrix, then you do that. So you see it's very fast and it represents all k-hop but in a more effective way. And also, if you want to analyze it theoretically, it's much easier to do that. So you know about feature propagation in graph convolutional networks. But the simultaneous update here for all nodes becomes a simple sparse matrix multiplication. So they are very equivalent. Then we have feature transformation and nonlinear transition, that after the local smoothing at GCN layer, you know all of these things. Then you give it to the classifier. But what about simple graph convolution? We hypothesize that the nonlinearity between GCN layers is not critical. This is an important statement. But the majority of the benefit arises from local averaging. We therefore remove the nonlinear transition function between each layer and only keep the final softmax in order to obtain probabilistic outputs, of course. The resulting model is linear, but still has the same increased receptive field. We are not changing the radius of this receptive field, we respect that, but we are removing the nonlinearity. So now we can analyze this much easier because it's just softmax of S to the k x theta. So we call it simple graph convolution. That's it. Then they do spectral analysis. So they say, oh, it's like a low pass filtering. It's like, for example, you have an image. If you do this, it's a low pass filter, it becomes blur. And you know these theorems that you see in classical spectral graph theory. So the feature which is under red and the filters which are in the blue, spectral coefficients for different propagation matrices on the Cora dataset. Also PubMed dataset, Reddit dataset. You can see how test accuracy varies with relative training time. For example, simple graph convolution has very, very low training time because you're just multiplying matrices, but the test accuracy is still almost the same as GCN, so we are not losing accuracy. That's good. And let's have a look. The hardest data set, as you observe, is this CiteSeer data set, which is 71%. Of course, this is in 2019, this paper. Now we have more than 90% accuracy. For CiteSeer, maybe because the number of nodes, number of edges, so that has some reasons that state of the art is not as good as other data sets.